Welcome back, everybody. So in this video, we are going to have our third statistics review. The topic of this video is measures of relative location. This is a super important topic. It's kind of a foundational topic because it's going to lay the foundation for the next and final review video, which has to do with hypothesis testing. Hypothesis testing is going to come up all the time in data analytics. And so these last two videos are super important because they lay the conceptual foundation for what we will do in data analytics. Okay, so with that introduction, let's jump in. Okay, so in the last video, we talked about variables. In fact, we did a demo from R, and we used a data set that included a variable called wage, and it was, hourly wages for workers in the United States. So we've been talking about variables, these mathematical objects that can take on different values for different observations, right? And in the last video, we talked about the idea of a probability distribution. Okay. We said a probability distribution is a function that communicates to us the probability that a variable will take on certain values or ranges of values. So we can think about it like this. What is the probability that a worker in the United States will have a wage of 3.1? Or we could phrase it differently. We could say, what is the probability that a worker in the United States has a wage between 3.1 and 3.5, let's just say. Okay. A probability distribution is a function that tells us that information. It tells us about the probability of having different values of a variable. It's a super important topic. We also mentioned this distinction. We mentioned a distinction between a discrete quantitative variable, I'll just write Q, a discrete quantitative variable, and a continuous quantitative variable. All right. So a probability distribution for a discrete quantitative variable, so let's just say a probability distribution for a discrete quantitative variable is a function that tells us exactly the probability of each discrete value of that variable. So for example, if I had a discrete probability distribution, if I had a probability distribution for a discrete variable, let's say the variable is education. How many years of education people have? Well, education, number of years of education will probably range from what, 0 to, I don't know, 26 maybe. That's an awful lot of years, but some people, sometimes people get multiple degrees. Um, but it's only whole numbers between 0 and 26. And so a discrete probability distribution would be a distribution that would tell us the probability that someone, let's just say in the United States, would have each of the possible values. Each particular value would be given a probability. All right. Now, for a continuous quantitative variable, what we're going to have is we're going to have a probability density function. Density function. So that is the probability distribution for a continuous variable is called a probability density function. Probability density function. And what it's going to do is it's going to tell us the probability of finding values within a given range. So it doesn't give us the probability of specific values. Instead, it gives us the probability of a range of values. Okay, but the basic idea remains the same. A probability distribution is a function that tells us about the probability of finding particular values of a variable, that's for a discrete variable, or a range of possible values, that's for a continuous quantitative variable. All right, and so in the last video, we talked about the observed or the empirical probability distribution for the wage variable. And so here it is. In fact, you probably remember seeing a graph that looks like this, right? This is the empirical probability distribution for the wage variable in the data set that we used, right? And so here, by the height of the graph, we are able to see or observe the probability of finding values of the wage variable in this data set. All right. And by looking at this, we can see, okay, very few people have wages up here near 25. Very few have wages down here near 0. A whole lot more people have wages here around, let's say, 4. Um, a decent number of people have wages here about, let's say, around 6. And as we get bigger, higher and higher wages, fewer and fewer people have those wages. And so this graph, the shape of the graph, the height of the graph tells us or communicates to us about the probability, how likely it is that a particular observation in our variable will have that corresponding wage. Okay, so that's review, but super important. All right. Now, you also remember from last time that when we have a variable, we can calculate certain basic statistics about that variable. So, for example, we can calculate the mean, right? We can calculate the mean. Or another way of putting that, another way of communicating that, another name for it is the expected value. Let's put wage in there. We could write the expected value, right? So this is a measure of central tendency or measure of central tendency. Kind of tells us what we would expect from a variable. Okay. And then we have measures of variation. So measures of variation include variance, standard deviation. Okay. Okay. And so we can calculate these basic descriptive statistics about a variable, and those statistics tell us something about the variable, right? The mean or the expected value, right? That's the same thing, mean or expected value. Um, it tells us a little bit about what we would expect to find from that variable. And then the variance or the standard deviation tell us a little bit about how much variation there is in that variable. You can also think about it as telling us how confident we might be that we would find whatever our expected value is. Okay, so we have these different basic statistics that we can calculate for a variable. All right. Well, let's say we calculated them. I'm just going to show them on this graph to kind of help us understand how they relate to each other. How do those basic statistics relate to the probability distribution? All right. So remember, here's our empirical probability distribution, so called the observed distribution of wages. This is a probability distribution. Just going to abbreviate probdist, probability distribution. All right, now we can calculate the mean or the average value of wages. And in this data set, the average value is 5.9. All right, and so that I just kind of, had it pop up there on the graph. And the mean is 5.9. So this is the mean. If you were to just pick someone out of the data set by random, you would expect to find someone around what this mean is. That's the expected value. Okay. All right. Now, we also can calculate the standard deviation. Now, the standard deviation is 3.7. Okay, standard deviation, that tells us something. It communicates to us information about how much variation there is in the variable. So the higher the standard deviation is, the more dispersed the variable is. The more likely it is that we're going to find values that are really far away from the mean. So for example, if our standard deviation, so I could like draw a graph. In fact, I'll show you this later. So here's a distribution. Okay. The higher the standard deviation is, the wider the distribution is. So here, the standard deviation is much higher than it is for here. All right, so the higher the standard deviation is, the more dispersed the values of the data set, the more dispersed the values of the variable are, and therefore the more likely it is to find values that are farther away from the mean. Okay. So that's what the standard deviation tells us. It tells us about how dispersed the data is. Okay. Now, another thing that's valuable about the standard deviation is we can actually see values according to how many, quote, standard deviations they are away from the mean. So, for example, in this distribution, the mean is 5.9. The value 9.6 is one standard deviation above the mean. The value 13.3 is two standard deviations above the mean. All right. So what I'm showing here is that values, certain values of the variable wages, can be measured in terms of how many standard deviations they are above or below the mean. Right? So here, I mean, we're just kind of doing the math. Like if the mean is 5.9, what value of wages is one standard deviation above the mean? Well, that's the mean plus one standard deviation. Right? So that's 9.6. So 9.6 is a wage of 9.6 is one standard deviation above the mean. Okay, now the reason I point this out, it seems almost trivial or kind of silly, like, well, yeah, of course. The reason I point this out is because what will become very useful, as you'll see as we go on, what is useful is that oftentimes it is valuable for us to know how far away a particular value is from the mean of a distribution. Like I might want to know, well, how far away is 20 from the mean? Or how far away is 25 from the mean? Or how far away is 0.01 from the mean? I might want to know how far away those are from the mean. And I might want to measure that distance, like how far away, let's just say, how far away is 20 from the mean? I might want to measure that in terms of standard deviations. Like I could do the math, like we could do 20 minus 5.9, like we could do that, but I might want to know what is or how far away is 20 from the mean in units of standard deviations. I might want to know how many standard deviations is 20 above the mean. All right, and I said, well, why would we want that? Why do we want to know? Why do we want to know how far away particular values are from the mean in terms of standard deviations? Well, the reason we're going to want to know that is because we are going to want to know um, how likely or unlikely it is to find values of a particular magnitude. So let me explain that. So if you look at this distribution, right, this is the distribution of wages. We saw this in the last video. One thing that you'll notice is as values of the wage variable get further away from the mean, they also become less likely. So for example, it is much less likely to find a value around 13.3 than it is to find a value around 9.6. You can see 13.3 is two standard deviations away from the mean, and it is less likely to find a value around 13.3. 9.6 is one standard deviation above the mean, and it is also less likely to find a value of 9.6 than it is to find a value at the mean. So my point here is that how far away a value is from the mean might tell us something about how likely it is to find a value of that size. And in fact, the more standard deviations you get away from the mean, the less likely it is that you will find a value of that size. Okay, that's going to be very important, right? I'm building up the building blocks here. Okay, why that's important is it's not yet perfectly clear, but I'm going to get there. Right now, suffice it to say that we are going to want to know how far away a value is from the mean in terms of standard deviations. And we're going to want to know that because the farther something is, the farther a value is from the mean in terms of standard deviations, the farther away it is, the less likely it's going to be. All right, and that's going to be very important. Okay, so there we go. Um, Let me just reinforce a couple of those points, and then I'll kind of go to the next step. All right, so here, a moment ago, okay, in this graph, I'm showing you the probability distribution of a particular variable in our data set, right? This is just to make it concrete. We saw this last time. You've generated a figure that looks just like this, okay? Um, Oftentimes when we do statistics, and we'll actually see this as we go on, we will be working with a very specific probability distribution. Okay. Now, probably the most common probability distribution we're going to be working with is called the standard normal distribution. The standard normal distribution. All right, standard normal distribution. This is a probability distribution for a continuous variable. So it's a PDF, a probability density function. It's a very nice probability distribution to work with. It's a very nice distribution to work with because it has a very clear, well-defined shape that has very nice properties. So if we look at this, this is called a standard normal probability distribution or probability density function. All right. For the standard normal distribution, all right, let's just say this is some variable x, and x happens to have a probability distribution that's a standard normal. The expected value of x is 0. All right, so it's a very nice property. So here, this is the average or expected value, and it's exactly 0. And also in a standard normal distribution, the standard deviation is equal to 1. So you can remember this. For a standard normal distribution, the expected value or the average is 0, and the standard deviation is 1. All right. And it's exactly symmetric on both sides. It's symmetric. It's exactly symmetric on both sides. And one thing you'll notice is that in a standard normal, it is much more likely to have a value close to the mean than it is to have a value far away from the mean. And the farther you get away from the mean, then less and less likely it is to find a value in that area. So for example, if we were one standard deviation above the mean, so that's here, my lines are not super straight. Let me try again. So if we were one standard deviation above the mean, you can see that it's less likely to find a value somewhere around 1 than it is to find a value somewhere around 0. And likewise for 2 standard deviations above the mean, and 3 standard deviations above the mean, and 4 standard deviations above the mean. You can see that as we get farther away from the mean, it becomes less and less likely for us to find values in that area. It gets extremely unlikely to find a value somewhere around 4. It is quite likely to find a value somewhere around 0, right? So the farther we get from the mean, the less and less likely it is to find a value in that range, in that area. Okay, so this is a standard normal distribution. We should feel very comfortable with these kinds of distributions because we'll see this quite a bit. So remember a couple things. Standard normal distribution, it is symmetric on both sides. It is centered at the mean. The mean is 0. The standard deviation is 1. You're much more likely to find values near 0, near the mean, than you are to find values that are really far away from the mean. Okay. All right. And as I alluded to earlier, I'm just going to kind of reinforce this here. The larger a standard deviation is, the larger the standard deviation is of a distribution or of a variable, the wider that distribution is going to be. So let me just kind of look at this for a second. So here, the red distribution, that has a standard deviation of 0.4, so it's a smaller standard deviation. And we can compare that, let's say, to the blue. The blue has a standard deviation of 1. So if you just compare the red and the blue, you will notice that there's much more probability density around 0 for the red distribution than there is for the blue. Likewise, there's a lot less probability density in the red distribution than there is in the blue distribution away from the mean. It means if you were just to do the comparison, if you had a variable and it followed the blue distribution, it would be much more likely to find a value around 2, for example, than it would be to find a value around 2 for the red distribution. Okay, so standard deviation tells us about how widely distributed the distribution is. So now here, just to be clear, here are 3 distributions. They're all symmetric, so they all follow that same symmetry. They all have a mean of 0. Now, only the blue one is a standard normal. The blue one here is a, quote, standard normal distribution, because standard normal has a mean of 0 and a standard deviation of 1. The other distributions here are they're just normal. They're not standard normal. They're just a normal distribution because their standard deviations don't equal 1. So they're not the other distributions that you see here are not standard normal distributions. They're just normal. All right, so there's a difference between a standard normal and a normal. A standard normal has an average of 0 and a standard deviation of 1. A normal distribution can have any mean and any standard deviation, but it has to have this shape, this symmetric shape where the greatest probability density is near the mean. Okay. All right, and here, just by comparing these, you can kind of see the effect that standard deviation has on a distribution. The larger the standard deviation, the more likely it is to find values that are further away from the mean. The smaller the standard deviation, the less likely it is to find values further away from the mean. It becomes much more likely when you have a small standard deviation, it becomes more likely to find values close to the mean. All right. All right, so I can just kind of reinforce this. So standard normal has mean 0, standard deviation of 1, 1 standard deviation, 2 standard deviation, 3 standard deviations, etc. Okay. All right, now, why does this matter? All right, let's go to the next step. So I mentioned earlier that we might want to know how far away a value is from the mean in units of standard deviations, right? We talked about that earlier. We talked about that when we were looking at this graph, right? This is our empirical probability distribution for the wage variable. And I was alluding to the idea that we might want to know how far away 20 is from the mean in terms of standard deviations. And the reason we said that was because the farther away a value is from the mean implies that it's less and less likely to occur. Okay. So what we're going to do now is I'm going to define something called a z-score. So a z-score is a specific number, and what it does is it tells us how many standard deviations a particular value is from the mean. So a z-score is exactly what I was saying earlier. Like when I said I wanted to know how far away 20 is from the mean in units of standard deviations, what I was saying was I would like to know the z-score that corresponds to 20. That every value of a variable has a z-score. The z-score is the number of standard deviations that value is away from the mean. How many standard deviations that value is from the mean, right? And that's what a z-score is. And we can calculate it. All right. This is the equation. It's actually pretty straightforward. Here I have a population version of it and a sample version of it. I think let's focus on the sample version. we're going to be able to calculate z-scores. And in fact, z-scores are quite important. All right. So if I want to know how many standard deviations a value is away from the mean, what I need to do is I need to take the value itself. So I'm just going to call that xi, a specific value. So when I was talking earlier about wages, my particular example was I wanted to know how many standard deviations 20 was above the mean. All right, so we could say xi is 20. That's the specific value that I'm working with, the specific value for which I want to know the z-score. Okay, then what you do is you subtract the mean, the average value. So earlier we saw that the mean was 5.9. Okay, and then you just divide by the standard deviation. All right, we saw earlier the standard deviation for our data set was 3.7. So you just do this calculation, and what this is going to do is it's going to tell us how many standard deviations xi is away from x bar. So let's do that math. We can do that for the example that I was given. We can have 20 minus 5.9 divided by 3.7. All right, so what we're doing here is we're calculating the z-score. Okay, so the numerator of this fraction is 14.1. We're going to divide by 3.7. And here is our z-score, 3.81. So what is that saying? That is saying that the value 20, a wage of $20 per hour, is 3.81 standard deviations above the mean. Okay, and again, why would I want to know that? Why would I calculate that? Well, the reason I would want to know that is because the farther away a value is from the mean, the less likely it is. And if I measure that in standard deviations, I actually can measure that in a kind of universally accessible way. All right. That means no matter what the variable is, I can calculate a z-score and I can compare them. I can look at this and I can say, oh, wow, 20 is 3.81 standard deviations above the mean. That's really far above the mean. That's a very extreme value. It is way bigger than the mean. If I just told you, okay, a wage of 20 and the mean is 5.9, it was like, well, okay, $14.1 an hour. I don't know. Is that a big or is that small? I don't know. But if you measure it in terms of standard deviations, you can know how much bigger it is. Like you can know, is it a lot bigger or a little bigger? When you see that it is 3.81 standard deviations above the mean, you can know that's a lot bigger. That is, it's almost 4 standard deviations above the mean. That's a lot larger. That is a lot larger than the mean. That tells us that $20 an hour in this data set, in this particular data set on wages, $20 an hour is a huge wage. It's a really high wage. That's very it's a very unlikely, a very low probability wage. It's really high. Okay. All right. So let me reinforce that a little bit because actually this measurement in terms of standard deviations, it's actually quite helpful. All right. So here we go. We can think about values of a variable using z-score. We can think about the values of a variable in terms of how likely they are using these units of standard deviations. Okay. Now, if a particular variable has if a particular value has a z-score that's around 0 or in between -1 and 1, or even like pretty close to -2 and 2, we can say they're fairly ordinary. Like it's not terribly unlikely that you would see a value in these ranges. It's not terribly unlikely. If a particular value has a z-score of 1.5, you say, okay, you know what? That's not terribly unlikely. Like that's reasonable. Like that will happen somewhat frequently to get a value around 1.5. Okay, that should be over here, right? Okay. And it doesn't even matter what the variable is. Like I could be talking about wages here, I could talk about experience, I could talk about education, whatever the variable is. Once I convert the values of that variable to a z-score, I can automatically tell how likely or unlikely the value is. So if a particular value of a variable has a z-score of 1.5, I know that's a pretty normal value. That's a fairly ordinary or fairly likely value. And certainly the closer it is to zero, the more likely it is. Once you get around 2 or above, or around -2 or above, then you start saying, wow, okay, actually, these are pretty unlikely. Like a z-score above 2. You look at that and you're like, wow, that's unusual. It's not very likely for that to happen. The probability to have a value of the variable that has a z-score above 2 or below -2, below -2, is pretty unlikely. Like that's kind of an extreme value. And if we have a z-score above 3, wow, like that's crazy. Like that's very unlikely. It's very unlikely to have a value above that is a z-score above 3 or below -3. That tells you that it's very unlikely. Okay, so what I'm saying here is that no matter what the variable is, no matter what the values of that variable are, if you calculate z-scores, you can know how likely or unlikely that value is. So now by comparison, now that we've looked at this kind of diagram here, when we see that a wage of $20 an hour has a z-score of 3.8, you can see that 3.8 and you can say, oh, wow, wow, $20 an hour, that's really high. That's like way high. That's really unlikely. In this data set, having a wage of $20 per hour, very unlikely. Okay. All right. So we're getting closer. We're kind of building up the building blocks here. All right. So now we have an understanding of these measures of relative standing. Okay, that's the z-score. The z-score is a measure of relative standing. It is a measure that tells us how far away a value is from the mean in terms of standard deviations, which gives us kind of a universal measure. We can apply this to any variable, and we will automatically know just by looking at the z-score how extreme or unlikely a variable is. All right, that's a lot. It's a lot of material here. Hopefully this is clear. What I'm going to do now is I want to relate this to something we talked about last time, which was this idea of the sampling distribution of the mean. All right, now this was kind of a complex topic. I'm going to review it a little bit. If you remember, if let's say we have a population of people and we want to know the average value of some variable for that population, right? So we have some population, let's say here's this circle, here's a population. What we would like to know is we would like to know the average wage for that population. We'd like, and so let's just say mu representing the average, population average for wage. We would like to know that. We would like to know what's the average wage in for all workers in the United States. But of course, we don't know wages on the whole population. That's way too many people. So what we do is we collect data on a sample, some small sample. That's that small circle there. I'm going to blow it up here. We collect data on a sample. Here's our sample. And what we're going to do is we will calculate the average wage. Whoops. We're going to calculate the average wage for our sample. And that would be called X bar. X bar wage, the average wage for our sample. And this average wage is our estimate of the population wage. Estimate. Okay. But what we said is that for every different sample we can take, there's a lot of different samples, right? For every sample that we take from the population, we're going to get a different sample mean, right? So if I took one sample, I might get an average of 5. And if I took another sample, I might get an average of 4.5. And if I take another sample, I might get an average of 6. And if I take another sample, I might get an average of 5.9 or 4.9, etc. Every time we take a different sample, we get a different sample mean. What that means is that X bar, the sample mean, is itself a variable. And with it, it has its own probability distribution. All right, so just kind of using the exact same scenario I used last time. Remember our sample of farmers, and somehow in this example, we somehow know the population mean, how large their farms are, 15 acres. But in reality, we would not know the population mean. So what we do is we take a sample. So here's one sample we could take, and we got a sample mean of 14 acres. Here's a different sample we could take. We get a sample mean of 18 acres. Here's another sample we could take, the red farmers here, for which we would have let's say a sample mean of 15.5, right? So every time we take a different sample, we get a different sample mean. Okay. So I want to connect these now. I want to connect what we talked about in terms of sample distributions, I'm sorry, probability distributions, and the sampling mean. Okay. So when you collect a sample from a population, and then you calculate in that sample, you calculate a sample mean. That sample mean is a particular value from the distribution of the sample mean. We call it the sampling distribution of the mean. That is, the sampling distribution of the mean is the probability distribution of the sample mean. All right, we call it the sampling distribution of the mean. This probability distribution, the sampling distribution of the mean, it is a normal distribution. Not a standard normal, it's a normal distribution. And the mean, the expected value of the sample mean, is equal to the true population mean. And the standard deviation of this sampling distribution of the mean is called the standard error. Right, the standard error, we oftentimes write that as SE with a little X bar here at the bottom, the standard error. And it's equal to the standard deviation of the variable X divided by the square root of the sample size. All right, that's review from last time. But what I'm doing here is I'm going to just kind of make that more clear. When we take a sample from a population and calculate the sample mean, that sample mean is going to be a specific value from this distribution. Maybe it's here. For example, when we did the blue farmers, this was where our sample mean was. When we did the green farmers, this is where our sample mean was. We did the red farmers, this is where our sample mean was. Now, typically in practice, we're only going to get one sample. And so we're just going to have this one, or this one, or this one. And this sample mean, this constitutes our estimate of the population, I'm sorry, our estimate of the population mean. Okay. So now, when we look at this, when we realize that the sampling distribution of the mean follows a normal distribution, there's a couple things that we should be able to observe. So one thing we would observe is that it is much more likely for our sample mean to be near the population mean than it is for it to be far away. So if the population mean is 15, our sample mean is I should say, it is much more likely that our sample mean is somewhere close to 15 than it would be for our sample mean to be somewhere really high, like 25, or really low, like 5. It's much more likely for our sample mean to fall somewhere close to the population mean than it is for our sample mean to fall somewhere close to 25, a really large number, or 5, a really small number. Okay. But it is possible that just by chance, our sample mean could be way out here. Or just by chance, our sample mean could be way down here. Both of those are possible. It's just less likely. It's more likely that our sample mean will be somewhere close to the population mean, aka somewhere close to the mean of the sampling distribution of the mean, right? Somewhere close to the center of this distribution. Okay, so every time we take a sample, that is, let's say we want to know something about um, all the workers in the United States. We want to know something about their wages. And let's say there's 100 million workers in the United States, and well, we can't collect data on all 100 million. And so instead, what we're going to do is we collect a sample of 526 workers in the United States, and we calculate the average or the mean wage within our sample of 526. That sample, that mean that we get, that we calculate from our sample, that mean that we get from our sample, that is our sample mean, is just one possible value of the sample mean. And that value that we get from our sample mean, which, if you remember, was 5.9, is a value from this distribution, this normal distribution. And the mean of this normal distribution is the population mean. Okay. All right. Okay, so I've been going back and forth here a little bit between the wage illustration and this farmer illustration. Let me jump back on the farmer illustration here just to be consistent. So here in this farmer illustration, we're saying we would like to know the average farm size of a bunch of farmers. We don't have data on all those farmers, so we don't actually know what the population mean is. Instead, what we do is we collect a sample of farmers, and it could be any of these samples, right? We just randomly pick a sample. So let's just say we pick the red one. We randomly pick a sample, and we get an estimate of 15.5 acres. And I'll give you another example of a different sample mean in a minute. All right. So we are going to collect data from a subset of farmers. So the red farmers here. Okay. And we're going to calculate a sample mean. And let's say that's what the sample mean is, 15.5. Now, we don't know what the population mean is, but we do know that the average value of the sample mean is equal to the population mean. It's actually what I should do here is I should just cover this up. We don't actually know this 15. We don't know the population mean. What we do know is that the average or the expected value of the sampling distribution of the mean is equal to the population mean. And we're just going to get one value, right? Because we have one sample, so we get one value from this distribution, and that's our sample mean. And we know what our sample mean is. So here's our sample mean, 15.5. All right. And what we can do is we can calculate, we can use the information that we have to try to understand how far away or how extreme of a value our sample mean is based on different possible values of the population mean. Remember, a z-score tells us how far away a value of a variable is from the mean of that variable. All right? And it tells us how far away it is in terms or in units of standard deviations. So we could actually kind of calculate a z. All right, we could say, here's our value, here's our sample mean, minus mu divided by the standard deviation of this distribution. Now, what's the standard deviation of this distribution? Well, we call that the standard error. The standard error is equal to the standard deviation of farm size, x, divided by the square root of the sample size. So we could, in theory, calculate the z-score for our sample mean. And that z-score would tell us how likely or unlikely it is to find a sample mean of that size. Now, in order for us to do that, we would have to know what the population mean is, and we would have to know what the standard error is. The standard error we can actually calculate. We have the equation here, but the population mean, we don't know this. And so in theory, we could calculate the z-score, but in practice, we don't actually know what the population mean is. All right. But for now, at least acknowledge, like, let's at least acknowledge that it could be valuable, at least theoretically, to know how extreme of a value 15.5 is by comparison to the mean. Now, in the next lecture, I'm actually gonna I'm gonna teach you a tool that we can use, even when we don't know what mu is, but I'm gonna teach you a tool to help us utilize this idea of a z-score to tell us something about how extreme or how unlikely our sample mean is, even when we don't know what mu is. All right, but I'll get to that in the next lecture. Okay. All right, so here I just want to kind of make a few points clear. So extreme sample means. So imagine instead that we collect a sample of data and we find a sample mean of 19 acres. All right. We want to know if this sample mean is likely or unlikely to occur. That is, we might want to know how extreme it is. But we technically don't know the sampling distribution of the mean, right? We only have one sample. So how would we know? How do we know if our sample mean is an outlier or not? Remember, we talked about how we can use z-scores to determine whether or not our specific value of a variable is an outlier, is extreme, is unlikely, or is it likely, right? We might want to know that. We might want to know how likely or unlikely our particular sample mean is. And this is where we use the z-statistic. We can calculate the z-statistic to help us determine how likely or unlikely our sample mean is compared to the mean. All right. So here's the z-score. We can calculate this. I wrote this on the board a moment ago, right? We just take our particular sample mean, subtract the population mean. This is still a question mark. I haven't answered this question mark yet. And then divide by the standard error. We know what the standard error is. We can calculate the standard error. All right. So we know what that is. We can calculate that. There's the standard deviation of the variable itself divided by the square root of sample size. Okay. So if we use this equation, if we use the z-score, we can figure out how far away our sample mean is from the mean, and that will tell us whether or not our sample mean is likely or unlikely. All right. Now, in some cases, when we do work like this, we might have a sample size that's not sufficiently large to use a z-statistic. This is going to feel a little bit arbitrary, but just bear with me here. The z-statistic is a statistic that we use to measure how likely or unlikely a particular value of a variable is, given its distribution, given its mean and its standard deviation, right? That's what we use a z-statistic for. In practice, we also sometimes use a very similar idea called a t-statistic. Now, a t-statistic is actually calculated in exactly the same way, but we use a t-statistic in situations in which our sample size is not sufficiently large. I actually don't need you to really sweat this difference too much. Just know that in practice, more often than not, in practice, when we are trying to determine whether or not a value of a variable is an outlier or not, we use a t-statistic rather than a z-statistic. All right, but it's actually the same idea and it's actually the same equation. Okay, so we're just gonna switch here. T-statistic or a T-score, we will use that to determine how extreme or how unlikely a particular observed value is of a variable. Okay, that's what we're gonna do. But I'm gonna cliffhanger you here. I'm going to show you, like if you remember, our T-statistic is equal to our particular value minus the mean divided by the standard error. We know this. We know this. Like we can calculate these, no problem. This is a mystery. That if we only knew what mu was, then we could say whether or not our specific value of the variable x, let's see, x bar, we would be able to say whether or not that value is extreme or unlikely or likely. Okay, and that's going to be really important to us. But in order to do that, we would need to know what mu is. We don't know what mu is, right? We don't now. In the next lecture, which you can see, that'll be the next video. In the next video, I'm going to explain how we can use this T statistic or Z statistic. I'm going to tell you how we can use this in a practical and powerful way, even though we don't know what mu is, right? Even though this is a mystery to us. All right, that'll be for the next video. I'm going to cliffhanger you here, and I'll finish up in the next video. All right, thanks everybody.